you're not later than Joe. How are you, Oliver?
Good, John. How are you?
All right. You know, if I were smarter, I would have just used my iPad.
To look at your notes?
Yeah.
Like, write on them?
Well, I would have put the current version of my lecture notes on my iPad, and I would just use that instead of these little scribbled horrible pieces of paper that I'm actually using.
That could have worked.
Maybe tomorrow.
Maybe the scribbles give you a certain kind of air of mystery.
You can also print your curve.
How?
There's a print.
No, that requires grappling with technology beyond a level I'm comfortable with.
If you need something printed, certainly, maybe there's a better way. I was printing things for David Simmons stuff in the first week by going up to my office and printing them at the printer there. So
they give out some cards to make it better.
Oh, okay. Good. We should give that to the speakers. One of many things for next year.
What's next year? What's the theme?
Actually, I probably should know, but I'm sure it's not stringy, so.
Is it up to you?
What's that?
Is it up to you?
No, it's not up to me anyway. Well, it's not up to anyone who is physically being. Tassie has a board, sort of like Aspen does,
I see.
and they make the decisions. Tom replaced KT, and I'll probably replace him as the local organizer, but we don't make scientific decisions. Sad.
I see.
And then the board decides who is going to be the scientific organizer, which is Joe. And Joe got Pedro to help her out.
Thank you.
You're welcome.
I've gotten pretty good at saying no to things.
Really? Well, you can say no if you want.
We'll see. We'll see if I'm up to it.
We have a center now.
Here?
It's called the Center for the Theory of Quantum Matter.
Cool.
It was mostly the condensed matter theorists who started it. Like Mike Hermele was, I think, the #1 driving force. But it's supposed to bring together people with interest in strongly coupled stuff across condensed matter, AMO, nuclear, strings. We've got a quantum information guy. I'm going to invite you to come speak sometime.
Okay. You know, we have a center for the study of fluids and gravity at the same time at UCSD.
Is that part of the official name?
That's the official name. Yes, I have. There's a webpage, and it's the funding for it is $16,000. Yours is probably more impressive from UCSD.
I had nothing to do with it. I can say how impressed I am with how they shook down different parts of this university for money.
I see. Cool. Should we start?
My meeting lady is coming out at your time.
Okay. Time to start now that Joe's here. Okay. So when we were most recently interrupted by the extremely rude continuous flow of time, we were in the middle of discovering how to emerge Z2 gauge theory from an extremely innocent-looking lattice model of spins, which is called the toric code. And it has a very simple Hamiltonian. The Hilbert space is a tensor product over links of some graph of a spin 1/2, a qubit on each link, and the Hamiltonian. So this is called the toric code, or rather the toric code limit of Z2 gauge theory. A toric code limit of a pretty generic spin system. And the Hamiltonian is minus a sum over the sites of some coupling times the star operator, and minus a sum over plaquettes times some coupling of a sum over plaquette operators. And so this gamma E and gamma M are some positive energies, and we put minus signs to encourage these things to be as big as possible. And let me remind you the form that they take. This is the product over links in the vicinity of the site of sigma z's acting on the links, and this is the product of links surrounding the plaquette of sigma x's. And this is a nice limit in the space of all possible ways to couple qubits on the links of a graph, because it's exactly solvable, because all the terms in the Hamiltonian commute with each other. And so we can find the ground state simply by diagonalizing each term individually, and each of these squares to 1, and so the ground state will be when each of them is 1. And we found that the ground states of the system, ground states, have the form, they're labeled by an element, let me call it alpha, of the first homology group of the space, which is triangulated by our graph. So this is, I don't know, let me call it sigma. What did I call it last time? I called it omega. Yeah, omega is the cell complex, and with coefficients in Z2. And this was obtained by taking a uniform superposition of states made from closed strings, where those closed strings were elements of that homology class. And so what I mean by this C is, well, let me just draw it locally. So let me remind you that if I don't draw anything, that's saying that Z sub L is 1. And if I do draw something, Z sub L is minus 1. That's a segment of one of these strings. And these C's are closed configurations. There can be as many of them as you want. They just can't end. And OK, so this is an extremely interesting fact. One reason that it's an interesting fact is that you can see immediately from this picture that this state has long-range entanglement. Here we go. Here's the picture. Let's draw some region of space, and let's draw some snapshot of one of the terms in this Hamiltonian, in this ground state. So the strings do something like this. They're all closed. Some of them are completely inside our region. Some of them are completely outside. But
Intersect, right?
yeah, that's a good point. They can yeah, actually okay, they can intersect. Yes, they can do that. If you study a trivalent graph, then they can't. It's kind of simpler. And if so you can always replace this by something like that, and then they don't really intersect. Yeah. Okay. Anyway, they can intersect, but it doesn't matter in this model. And I'm drawing a two-dimensional picture here, but that it's actually what I'm saying is actually not special to 2 dimensions. And the important point is simply the following thing. Suppose I ask about the entanglement entropy of the reduced density matrix of this state for this subregion. Then I can have strings here. I can not have strings here. Nobody in here cares. I can have strings here and not have strings here. That doesn't contribute at all to the entanglement. The only thing that contributes to the entanglement is the strings that cross the boundary. And so of course there's an area law term from all of these links that are crossed by the boundary. So there's a contribution proportional to the area. But then there's one extra thing that we know about the outside, given the state of the system on the inside, which is that if a string goes in and it's closed, it has to go out again. And so there's one bit of you can have even number of them, but there can't be an odd number of strings crossing this boundary. Okay, so there's one bit of information missing. And so the entanglement entry is actually this minus log 2 from that one extra bit. And this is the thing I called gamma. It's the topological entanglement entropy of this ground state. Yeah, it's very, very simple. Okay, so this is a state with topological order. It exhibits this phenomenon of long-range entanglement. And I guess the important thing I should emphasize is, it's independent of the size of the region. You make the region bigger and bigger, you still know that there's an odd number of strings crossing the boundary. Okay, and another important feature of these degenerate ground states, which you might say, I told you that degeneracy is something that needs to be explained. And you might worry that this degeneracy is just because I chose such a special Hamiltonian, and it'll go away if I perturb it even a little bit. This degeneracy is in fact very robust, because there's no local operator such that acting on one of these ground states gives me another one. I know this because I know a precise set of operators that maps them to each other. They're very simple. They're just the Wilson loops and the 't Hooft loops. So let's define for any curve C, WC, to be a product over links in the curve. So this C is a curve in the lattice, so some sequence of links whose endpoints cancel out. Yes, please.
How are you defining local? You don't mean like at one link, right? But it's some small set of
Yeah, I mean
links,
some set of links
something
which
that
is
doesn't scale with the size of the system or something.
Precisely. Yeah, order L to the 0, exactly. And I guess when I say that, I'm also assuming that I'm scaling the whole system up, right? So in fact, you could imagine if the space you were triangulating were some gigantic space which had a very tiny handle, and you take the thermodynamic limit by making this space really big and fixing this handle, then I'm going to show you that this operator will mix some of the ground states. But that's cheating. OK, so associated to any curve, we're making an operator which is the product of these x's. And according to the cartoon of an equation that I wrote last time, you should think of this as the line integral, the line integral with the pretentious circle on it, around this curve of this gauge field. All right, so this is a Wilson loop around that cycle. And there's another operator that we can associate to a similar picture. So here's, OK, so this is let me draw a piece of our completely generic graph. And so C is a curve that looks like this. It's a bunch of these links. Let me not say whether it's closed or open yet. And then there's another kind of curve I can draw, which is going to be interesting, which is I can draw, if I draw a path in the dual lattice. Actually, here I'm. OK, let me specify for a moment to the case of d equals 2 plus 1, so I can draw the pictures. In that case, associated to any cell complex like the one I've drawn, right? So I define this thing to be some bunch of cells of various dimensions up to d. Associated to any such thing, we can construct a dual complex. This is, I guess, Poincare duality, where omega hat is just the original omega d minus p. Here's the idea. So for associated to any site of the original lattice, so this S is an element of omega 0 here, there's a plaquette of the dual lattice. This is in the case with d is 2, and so d minus 0 is 2. And associated to any plaquette of the original lattice, there's a site of the dual lattice. Right? So we interchange, in 2 dimensions, we interchange the sites of the original lattice. The sites of the original lattice are plaquettes of the dual lattice. The links of the original lattice are links of the dual lattice. They correspond to each other. And the third thing. OK, so if I draw a path in the dual lattice like this, I can look at the set of links in the original lattice that are crossed by it. Right, so these are the links in the dual lattice that correspond to these links. Oh, they're dotted. These links in the dual lattice. So this is C check, I'm going to call it, for a path in the dual lattice. And associated to that path, I can define, let me call it V, C check, to be the product of links, I guess I should say crossed by, links crossed by C check of Z sub L. OK, so this is some set of operators. And why am I telling you about them? Well, I'm telling you about them because, first of all, if these paths are closed, if the boundary of C is 0 and the boundary of C check is nothing, so that the path closes on itself, then all of these guys commute with the Hamiltonian. You can see this because they commute with every term in the Hamiltonian. And in fact, the plaquette operator, V sub p, is itself one of these. It's just W for the case where C is the boundary of the plaquette. Right? It's the product of x's around the plaquette. OK, so that's the sort of special case of this statement. So this is a huge bunch of symmetries of this Hamiltonian. And what is the significance of it? Well, one significance of it is the following. Suppose we consider the particular ground state of this form, which is associated with the trivial cycle, okay, where I only sum over paths which are contractible. Okay, so let's call that, 0 is sum over contractible paths, uniform superposition. Then, and suppose I'm on a space which, suppose it's the torus. I claim that by acting with this operator I called W don't know, I need a name for this guy. Okay, let's call that guy alpha. W alpha on this state, I get the state I called alpha. I guess here it's the homology class. Right? Because this operator is a product of x's along that path, and an x acting on a link flips the z eigenvalue. Right? So if there were no electric flux there, it would turn some on. And so this thing creates, it basically just creates one single string there if there was none there. And so this creates a uniform superposition of loops in this homology class. Okay, so this is the operator that mixes these states. But it is a non-local operator. It's a Wilson loop. Okay, and I guess there's one more thing I should say, which is that these VC and VC check and WC don't commute with each other, right? So this is an example of this argument I used in the Chern-Simons case, that these operators fail to commute if the two paths intersect an odd number of times. Because if the two paths intersect an odd number of times, I don't know, so let's think about this. This is C, this is C check. They intersect on this one link. That means they share, this one has a single x for this guy and a single z for this guy. And those things anti-commute. There's a single term that doesn't commute, and they anti-commute. And this algebra is represented on the ground state because of this fact. They commute with the Hamiltonian, but they don't commute with each other. And they form this, sort of Clifford algebra thing. Not Clifford. It's, just anti-commutator. They anti-commute. Okay, and so the number of ground states in this case, well, I mean, you can see it from that expression already, is 2 to the b1 of space. Okay, and now there's one more reason that I mentioned these line operators, which is if we consider instead open Wilson lines, suppose the boundary of C is, I don't know, P1 minus P2, 2 points. So here's C. This is P1, and I don't know, let's send this guy off to infinity. Then think about what happens when I act with WC on any one of these ground states. Well, at the end point here, we have a single x, right? There's an x sub L acting here, right? And that acting with an x sub L flips the z on this link, but none of the other ones. And so if this state satisfies satisfies a sub s equals 1, right, where s is, s is, I shouldn't use p to label points. Okay, p is for plaquette, s1 minus s2. A sub s1 gives eigenvalue 1 on this ground state, but now if I act with this on this state, these two anti-commute, right? Because this one has a z and this one has an x, and so this is minus WC. Yes, this is an excited state where we violated the star condition at that one site, and so this thing has energy 2 gamma e above the ground state, right? We flipped a single one of these guys. Except there's another end of the string, and so it's 4 gamma e because we violated 2 sites at a time. Okay, and there's no way to violate a single site on a compact space because there's always another end of the string. Okay, if I act with the x here, I'll move the defect from here to here. Right? There'll still be an end of the string. You can't get rid of it. Similarly, if I act with v c check and c check ends somewhere, this thing satisfies bp equals -1 for some choice of p that you can figure out. Okay, so this is called an electric defect. It's an electric defect if you think of a sub s as the Gauss law constraint. So violating means that you have some charge, electric charge. The strings can end there. That's Gauss's law. And the violation of this condition is a magnetic defect in the sense that this is like creating some magnetic flux on this plaquette. Right? It's like putting pi flux on that plaquette. Okay. And the significance of the fact that it's these string operators that mix the ground states, and these string operators that are the operators which adiabatically transport the quasiparticles around these loops, that accounts for the stability of this degeneracy. So now let's think about what happens if we perturb this system, for example, by some terms like, which one is g? H times x plus g times z. right? So these terms are going to make all kinds of trouble because this thing creates a pair of defects on the two sites whose ends are this link, and this thing creates a pair of defects on the two plaquettes that are shared by this link. And so perturbing by even some small coefficients here is going to produce some gas of defects, which can move around because this x is like a kinetic term which hops the defects across that link, hops the electric defects. And so what happens? Well, okay, to see that eventually something will happen, let's study the case where we make G so big that it's bigger than gamma E. So it overwhelms the star condition. Okay? This is a very extreme thing. We're turning on this big... do I want to turn G or X? Yeah, let's do G. Okay, let's think about that. And let's think about... So in this limit, the ground state is instead, well, this term is the biggest. You want to make this thing happy, right? You want to make that happy first. It's approximately just a product state, right? Each link wants to have Z sub L equals +1 so that if G is positive, you minimize this term. Right? So that's just a product state, and it's the product state where there's just no electric flux. Right? There's no lines of flux. That's this statement. Right? All Z equals 1 means I don't draw anything. Okay, so this is an extreme limit. And suppose now I ask about the force between charges in this limit. Suppose I demand that at this site I have A sub s equals -1. This as an external condition. And demand that here I have A sub s equals -1. This is like inserting an external charge in the gauge theory. Right? I'm putting this there, and I'm asking, what is the lowest energy configuration of the gauge theory in this situation as a function of the separation between them? And well, the fact that you have A sub s equals -1 here means you have to have some electric flux coming out of here. Right? There has to be one of these, an odd number of these has to have Z equals -1. So there has to be a flux line, despite the fact that this thing really doesn't want it. Right? This thing costs some energy. And so you can see that you have to root some string between these two things. And the energy is in this extreme limit is just you want to minimize that length. It's proportional to the number of times you violate this term. It's 2g times x, right? Where x is the minimum length where you take the straight line. Okay, so this is saying that there is a linearly growing potential between the two external charges. There's a constant force. What is the name for this phase of the gauge theory? It's confined. That's right. So the external charges are confined. Okay, so that's the extreme limit where we turn it on really big. So we know that'll happen eventually. So what happens if we turn it on just a little bit? And the best way that I know to answer this is to construct an effective field theory. And here's the answer for the effective field theory, a sketch of the effective field theory that governs this the system with these couplings. It looks something like this. Well, what do we know about it? We know that we can create an excitation which is an electric defect, which is a particle. Right? It's a localized object. It doesn't have a completely independent life of its own because it has this string attached to it. And we can create a magnetic defect, which is also a particle, even though it lives on a plaquette. And something we know about them is that the creation operators for these objects don't commute. So this V is the thing that transports a magnetic defect along this path, and this W is the thing that transports an electric defect along this path. And this statement, that if those paths intersect an odd number of times, says that these particles have some non-trivially mutual statistics. In fact, it means that minus sign means that they're mutual semions. And so they're not just the fields that we're going to introduce to create these particles are not completely independent. And yes, well, it means that the mutual statistics is -1. It means you get a -1 if you move them around each other. Yeah, it's like half of a fermion. Yeah, but they're mutual semions, right? So each of them on its own is just a boring bosonic object, right? And it's only this one sees the other one as a semion. It's like some kind of funny marriage, yeah. And but we know how to change the statistics of particles in 2 + 1 dimensions, right? We stick a Chern-Simons term. But if we couple each of them to a gauge field and add a Chern-Simons term for that gauge field, it'll change the statistics of the particle with itself, right? So that's not quite what we want to do. Yes, please. Yeah, the end of the string, exactly. Exactly. The reason we can call it a particle is because in the phase that we're discussing over here, these strings carry no tension. They just flop around. And so the only place where the energy is localized is at the endpoints. So it's really a localized excitation. It's in this extreme other limit that the string has a tension and the particles only live at the ends of the strings.
Okay, I mean, I could have two strings. One of them could be going around the other one, or it could be.
But the ground state is the uniform superposition of them. Yeah, I'm talking about low-lying excitations above this ground state. That's right. Yeah. So I'm trying to construct an effective field theory for the low-lying, low-energy behavior. And actually, really, the main thing we're going to use it for is to understand the phase diagram. Right? OK, so it's not just that we want to add a Chern-Simons term. There's another hint for what we want to do, which is that this model conserves parity. If you reverse all the directions, you get back the same thing. Whereas the Chern-Simons term gets a minus sign when you do parity, right? Because you got, it's a form. So if you reverse the orientation of space, if you take your right-handed system and look at it in the mirror, you get a minus sign. And so that also doesn't work. So does anybody know how do you make a theory with Chern-Simons gauge fields, but which is parity symmetric? Yeah? Non-simple gauge group. I guess, yeah, that is a good ingredient. Yeah. Suppose U1 squared is an example of a non-simple gauge group. That's the one we're going to think about. Yeah, so, yeah, there you go. All right, so you people should know about this from the ABGM theory, right? Where you have two kinds of Chern-Simons fields where there is a mutual Chern-Simons term. So A has it says that the flux of B gets attached to the charge of A. Here, let's write integral of k over 4 pi. And then B, the equation of motion of B, says that the flux of A gets attached to the charge of B. Okay, so they are mutual Chern-Simons fields. And then we're going to minimally couple some ordinary fields. I'll write a little bit of a cartoon of what I mean by this. So there's a field E, which is charged under A. So I want you to think of A as like the electric gauge field, and E is not the electric field, but it's the operator that creates an electric defect. And there's another operator, which I'll call M, which creates a magnetic defect. M is for magnetic, and it's charged under B. And then there's some potential for E and M, which I guess it should be gauge invariant. And then there's a parenthesis. OK, so the potential is the thing where most of the information about the phase diagram is going to go. But already, this Lagrangian will encode the mutual statistics that we need. Right? It says that if we have an E particle, it's charged under A. And then the equations of motion of A attach flux to it. And so if we choose the right value of k, which is actually 2, I think, we can make them semions. If we choose the bigger value, we'll turn them into some word that means a smaller fraction, ons. Yeah. OK, and so then what should V be? Well, here I'm going to channel Landau and Ginsburg and just write all the stuff that we can write. So there's some term which I'll call R sub E, which is like a mass for E. There's an R sub M, which is like a mass for M. And then there's some self-interaction for E, which you know that it should be because you can't have two E's on top of each other, right? Because if you act twice with any of these things, you get back nothing. So there's definitely some short-range repulsion between two E's. Similarly for the M's. And then we can also have some interaction between the E's and M's. And then maybe there's some other terms that I'm forgetting. OK, so but here, this includes the important things. And then I claim that you can understand the following phase diagram. So this is like G, and this is like H. And I claim that the point where G equals H equals 0 here is, which is the toric code point, is the point where R sub E is plus infinity. So this, I guess, sorry, it's actually R sub E should be proportional to 2 gamma E. That's the energy to create a single electric defect, right? It's like the rest mass of the defect. And and also the defect can't move, right? So I guess also in the coefficient of its kinetic term, we should include some coupling that I'm not going to write. Okay, so that's the toric code point in this phase diagram. And as I go in this direction, we said that basically what's happening is that these electric defects are becoming lighter. They can hop. The states of the electric defects sitting at different places mix with each other. They'll form some dispersing band, which has some minimum, and they'll have a finite mass in finite kinetic terms. This is the mass of the electric defects. This is the mass of the magnetic defect, mass squared. And as you make this coupling is bigger and bigger. They can move more and more. Here, let me draw a picture of the band that I'm talking about. This is a picture of momentum. This is a picture of energy. And at g equals 0, here's the ground state. That has, I guess, sorry, the ground state is here at 0 momentum. But then at g equals 0, the defects are completely localized. Right? The state of a bunch of defects sitting anywhere has the same energy. Right? So I could also make momentum superpositions, and any momentum would have the same energy. But as I turn on g, instead, it'll split this band. I'll get some nice dispersion, which will have a minimum. And this minimum is something like g. Is something like g below this, and this energy difference is 2 gamma e, the energy cost to make a defect. And as you make g bigger and bigger, this bandwidth gets bigger and bigger, and at some point it'll hit 0. The electric defect will become massless. So there's some special point here where Re is approximately 0. All right, that's when this mass term goes away. And similarly, there's some special point here where R sub m is approximately 0. And we know for sure there's some kind of phase transition where here the electric defects will condense. What happens if I have some electrically charged field coupled to a gauge field and it condenses? What happens to the gauge field? Really? You're not gonna? Huh. I thought you were on my side. Okay. Well, yeah, so there's this Anderson mechanism, this Anderson-Higgs mechanism, and so over here is a Higgs phase. And what happens if we make, oh, sorry, I said this wrong. I got this wrong. Maybe that's why you're being quiet. Because, H is the thing that makes the electric defects lighter. That's the thing which gives the kinetic term. This is like the kinetic term for E. And this is the kinetic term for M. Right, so condensing the electric defects is going this way. So this is the Higgs phase. And what happens if we make G bigger? Over here is this was the calculation that we did over here. This is where the string tension is big. This is confinement. And this is where we get, if I tell the same story with the magnetic defects. This is condensation of magnetic charge. It's this classic picture of what confinement should look like. And OK, so something happens in between, which you could figure out based on this sort of mean field picture. And actually, if you choose these coefficients to vary in some reasonable way with what you think, how you think they should depend on G and H, the picture looks something like this. These two lines of critical points, this is condensation of some charged field. This is condensation of some charged field. This is a pretty boring critical point. There's a little bit extra. They end in a multi-critical point, which is also the endpoint of a line of first-order transitions, at the end of which there's another multi-critical point. Okay, so this is also known for numerics. And these special points are sort of part of my motivation for telling you so much about this, lie on a certain line in this phase diagram, which, if my drawing isn't that bad, is the fixed locus of a certain operation that you might be tempted to do on the couplings. And on the names here, right? So there's this, right, okay, so, yeah. So this model has actually an exact electromagnetic self-duality. If gamma E and gamma M are equal. So I'm assuming here gamma E is equal to gamma M. And the only thing that can break the duality symmetry is G and H. And if G and H are equal, then there's an exact self-duality, which is just this map. You just replace the sites of the original lattice with the plaquettes of the new lattice, and interchange what you call electric and what you call magnetic. And these critical points are along this self-dual line. And the reason I'm telling you about them is because they actually represent some very interesting scale invariant field theories, which have the property which is somewhat rare in our understanding of the world. I guess maybe the first place that it came up is in Argyris-Douglas points. That's the most explicit, well understood example where there's a gauge theory where there are light degrees of freedom carrying electric charge and light degrees of freedom carrying magnetic charge at the same time. So this makes it very hard to write a Lagrangian description for it, at least in 3+1 dimensions, because you can't use the vector potential if there's light magnetic charge, because it's not smooth. And here's this thing. So this line is where electric charge condenses. This is where magnetic charge condenses. And on this self-dual line, they both have to condense at the same time. And so these two critical theories are some very interesting new kind of fixed point, maybe CFT. I don't know if it's a CFT, which is really very poorly understood. But a starting point for studying it is just this Lagrangian, where you tune these coefficients to 0 at the same rate, and to find this line of first order transitions in the phase diagram, you also have to tune this V. And so there's some special potential that describes these 2 points in the space of couplings, which is some scalar fields coupled to mutual Chern-Simons theory. It's very similar to the kinds of field theories that on which a lot of work has been done in the recent high energy literature. And it's realized in the phase diagram of this very simple spin system. So this is something we should understand a lot better than we do. OK. OK, so I guess maybe the only other thing I want to say about the Tor code is although I've focused in this discussion on 2+1 dimensions, the definition of the model and much of the structure of the physics is the same in any number of dimensions. Yes, please.
What would Katea's motivation for constructing it?
It would probably be a mistake for me to attempt to understand what was going on in his mind. But one thing he definitely says is, and the reason that it's called a code, is that it's a way of hiding quantum information from local disturbances. Right? So this fact that no local operator distinguishes this ground state means that if you have a quantum system realizing this phase and you couple it locally to some environment, the environment can't measure the quantum state of the degenerate subspace.
Z's and X's are actually easily realized in quantum gauge.
Well, yeah, they're just single spin operators. That's right. And I guess I should mention people have actually made this system out of superconducting, Josephson junction arrays. It's pretty impressive. Yeah, there's a lot more to say about that motivation, but maybe I don't want to say too much. Okay, but that property, the fact that local operators don't measure the ground state, is the thing that makes it stable. It's the reason that there's an open set in the phase diagram, which is this. I should have emphasized more, is this topologically ordered phase. Okay. The challenge in higher dimensions is that the magnetic defects no longer are particles in higher dimensions because they live on d-1 cycles, which is no longer equal to whatever it's equal to here. The codimension is bigger. OK. Great. Right. Right. Well, okay. So I don't know that you should, but it may be occasionally useful to you to know that there is the same kind of construction where the Gauss's law for the gauge theory is realized as an energetic constraint rather than as a hard condition in defining the Hilbert space, can be generalized to other gauge groups. So in fact, there are attempts to realize continuous non-abelian gauge groups in this way. It is possible. It works in the sense that it's possible to argue that they're in the same way that in the regime where if I let gamma E be much bigger than gamma M, then in this regime below gamma E, this is energy. This thing is Z2 gauge theory. And then here is the gap. It can accomplish the same thing. I don't know if it's useful for learning about QCD in particular, but yeah, the same kind of construction can work. I guess people have been trying to take advantage of this possibility to do quantum simulations of QCD, to realize this kind of phenomenon in some like cold atom system where the interactions between the atoms are chosen to do this emergent phenomenon, so that you could just do some measurement and it would tell you the pion mass. It would be cool. Okay. So this was part one of Whence the Gauge Fields, and it was a little bit of a detour from the inexorable path of progress that we were taking towards understanding quantum Hall physics at every level of description. So now I want to return to that. Return to that path. So we're going to do Whence the Gauge Fields part 2, and this step will be a little bit less well controlled, for better or worse. I want to talk about the parton construction, which is a very good way of discovering new phases of matter with gauge fields. It's a little bit less under control, but it has the advantage that it suggests very nice trial wave functions, which you can then check. You can do variational calculations. Okay. And so we can understand the Laughlin wave function this way. So this is whence the gauge fields part 2. And I guess maybe the way I should try to catch your attention in this subject is to say that the thing I'm describing is a duality. It's a duality between some lattice model of electrons and spins, or electrons or spins, or some kind of SOD model like I've been talking about, and a gauge theory, and a lattice gauge theory. Okay, so the idea is it's a duality, between the SOD model and lattice gauge theory. And okay, let me just tell you how to do it. So it has two parts. Step 1 is kinematics. And the kinematics is, so this is analogous to the part in checking cyber duality where you check the anomaly coefficients. So you want to check that it's living in the same Hilbert space is maybe the better way to say it. So this is so suppose we have some Hilbert space, which is defined in the way that I've been discussing, and I want to, instead of using the variables like the z's and the Pauli matrices acting on the spins, I'm going to use some other set of variables which may have some redundancy. And actually, the example I'm going to think about is not spins, but let's really think about electrons. So here, let me write the example over here. Suppose we have a Hilbert space which carries a representation of a bunch of electron creation annihilation operators. So let's think about spinless electrons, with annihilation operator Ci. And so they satisfy one of these things. Canonical anti-commutation relations at different sites anti-commute at the same site, they anti-commute to 1. Notice, by the way, that the Hilbert space that represents this is not actually a tensor product, because the operators far apart don't actually commute with each other, right? So this is it's a small deviation. It's a funny kind of fermionic SOD. We'll let this slide. And let's consider, just for example, just for definiteness, because some people get nervous if they don't know what the Hamiltonian is. Some sum over links of some lattice of some hopping term. So this is a term which annihilates the electron at J and puts it at I with this amplitude. And I'll choose an interaction term which is also between neighbors. So V is some positive thing which says that, so this Ni is the density of electrons at I. And this is because they're spinless, this is only 0 or 1. And so it squares to itself. Right? And so having ni squared wouldn't do anything. So it's not possible to have a on-site interaction between these things. And so this is, if these are neighboring sites, this is the shortest range interaction they can have. And and let's imagine, I'm not going to say more about this, but let's imagine that these hopping amplitudes include some magnetic field. So, why is the electron spinless in the first place? Maybe it's because it's in a big magnetic field, and so the spin up state is low energy, and the spin down state costs lots of energy, and we can forget about it. And let's suppose that this magnetic field is visible still in these hopping amplitudes, so that this is there's some magnetic flux through each plaquette, let's say. Some fixed flux through each plaquette. So this is some lattice model of electrons in a magnetic field with some short-range repulsive interactions. Okay, so this is some well-defined model which maybe we'd like to understand. And I guess I also need to tell you what the filling is. I need to tell you how many electrons there are, which we'll come back to. Actually, you know what? Let's suppose that let's suppose that there's 1 electron for every 3 orbitals, for every 3 low energy orbitals. So that's called filling fraction of third. So this is the example I want to think about. And so that 3 is going to lead me, with a lot of hindsight, to write an equation like this. That I want to rewrite the electron operator at site I as a product of 3 things. Okay, so this is 1, this is 2, and this is 3. So these Fs are 3 new kinds of fermion operators. They annihilate 3 new species of fermions at the same site. And I'm imagining that when I create an electron, it creates one of each of these things. And the fact that the electron is a fermion means that these things had better be Grassmann if they're all the same as each other, right? So that 3 of them is still a Grassmann operator. And let me rewrite this in a fancy way as epsilon alpha beta gamma, F alpha, F beta, F gamma. And the first thing that maybe you'll notice about this is that there's a huge redundancy in the description I'm making. Namely, there are many states of these Fs that I can make by acting with these Fs that are not states that I can make by acting with the electron. And one way that we can notice that is if I take F1 and rephase it by some phi, and take F2 and rephase it by the opposite phi, and do nothing to F3, then nothing happens to C. Right? So this phase, this phi phase, just is a gauge redundancy. And similarly, there's one where I take, if I do that, the same thing, replacing 1 with 2 with 3, it's another redundancy. And in fact, as I've written it, there is an SU3 redundancy where F alpha goes to some U alpha beta, F beta, where U is an SU3 matrix, right? And the determinant had better equal 1 because if it's not, then that'll change the electron, right? So this is like a baryon, right? It's like a baryon invariant of SU3. So you should think of this first step as imagining that there's a gauge theory. It's a gauge theory in the sense that the Hilbert space had better be the Hilbert space of the Fs modded out by this redundancy, where the electron is a baryon of these charge degrees of freedom in that gauge theory.
Do the Fs satisfy normal anti-commutator relations?
Yes, good. So in fact, it's a tricky business, a slightly tricky business, to make sure that given that the Fs satisfy ordinary anti-commutation relations, that equation implies that the C's do too. So this is a little bit of an algebraic fun exercise, which I will not do. But indeed, you want to make sure that the Hilbert spaces are the same. And one way to do that is to do something, I guess you could think of it like Gupta-Bleuler quantization, where you impose the Gauss's law as a physical state condition. I did.
You can have things where you excite one F but not the other.
Exactly. And now I need to small in it again. Yes. Okay, so we ensmallen it by imposing what I want you to think of as a gauge condition, which is that F1 dagger F1 minus F2 dagger F2 is fixed, and it has to be fixed to be the same as C dagger C. This is for all I. So everything in this equation has an I, a site label, and at each site, the number of electrons, this is the number of electrons. No, this is wrong. This should be 0. Sorry, this is 0. And that's because in states that I can make with the electron creation operator, the number of electrons is always the same as the number of each of the 3 partons, right? So the states that Oliver is talking about, we can't have. Right? So the number, I'm in the black hole. C dagger C is equal to F1 dagger F1 equals F2 dagger F2 equals F3 dagger F3. Right? Because C dagger creates one F1, one F2, one F3. Okay, and so we can impose instead these 2 conditions, which you could think of as choosing a Cartan subalgebra of the SU3. And introduce a Lagrange multiplier, which imposes each of these constraints, which is like the time component of the gauge field. And then where does the spatial component of the gauge field come from? Well, one way to think of it is, perhaps a more practical way, is to say, I want to write down a gauge covariant action, or a gauge covariant Hamiltonian for my partons. And to allow them to hop, I need to have some connection between the sites. So I better have a spatial component of the gauge field. You buy that? So an alternative argument that some people find more convincing is instead to think about this interaction term. So this interaction term up there is C dagger C, sum over I, C dagger C. Okay, and now let's rewrite this in terms of the partons. I'm going to rewrite it as, in terms of the average. So I'm going to write it as sum over I, V, 1/3, sum over species, F dagger F. That's the density. 1/3, sum over beta, F dagger F, J, beta. All right, so I'm rewriting the density in terms of the partons. And now I'm going to use this completing the square trick, which is named after Hubbard and Stratinovich, which decouples this thing by introducing some auxiliary field, a complex auxiliary field, which looks something like this, alpha beta. And this thing also has alpha beta indices. Alpha beta run from 1 to 3. So this is like in the adjoint. There's a 1 over V here, and then, okay, so maybe, well, and then I'm going to take one of these guys from here and one of these guys from here. So this is, okay, there's a sum over ij. Fi alpha dagger F j beta. Okay, and this is, who is this summed over? It's the same sum. And then maybe there's a 3 somewhere. Do you guys buy this? And plus Hermitian conjugate. So if you complete the square here, it sets eta equal to this combination of things. And you do the integral over eta, it evaluates to the square of that thing. With some reshuffling, it turns into this. Maybe there's a sign somewhere. Okay, so now look what happened. If I rewrite, please. Yeah. Yeah. That's right. That's correct. That's correct. That's correct. Yeah. So the only place where the 1/3 came in was my initial guess for what relation I should use between the partons and the electron. Well, some information about the form of the interactions came in here. But we'll see. So there's a check that we're not doing something crazy. All right, let's go here. Yeah. Hubbard V. Where's the theta? Where's the theta? Oh, this A here. Yeah, oh, sorry. Yeah, I should have drawn it as the same kind of external A that I used. It's a fixed external variable. Yeah, just a bunch of numbers determining the band structure. That's right. OK. Yeah, please don't get too distracted by the specific model. It was maybe some misguided attempt to be a little bit concrete. It's a little hard in this business. So now look at this expression. And let's extract the phase of this variable eta. Yeah, I shouldn't. This A is not. This is an external gauge field. This A is the A that we're looking for. So this Aij is a phase. It's a variable living on the links, and it appears multiplying this term which hops the partons. And so if I can convince you to ignore this amplitude degree of freedom of this eta field and just set it to a constant, which I encourage you to do, then the model that we get looks like a Hamiltonian for the partons, which is a hopping term determined by this eta, the magnitude of eta, times fi alpha e to the I a ij alpha beta. There's a dagger fj alpha beta. And that's the end of it. All right, and then there's some. I guess I'm imagining that we've done the integral over eta and evaluated it at its saddle point. And so this thing determines the hopping amplitude.
What happened to the original hopping term for the C's?
Well, good. So you're right. So if I plug in the f's there, that turns into some horrible fourth order, cubic interaction between the, many body interaction between the partons that I'm going to ignore.
Right. I guess you're not imposing that constraint directly in the Hamiltonian.
Constraint? Which constraint?
Well, the C dagger C equals F1 dagger.
That's only this is important. It's only if they have if they're on the same site. It's the number. Yeah, those are on different sites. Yeah. Okay, good. So So now we come back to your question. Okay. Yeah. Exactly. Exactly. There's no kinetic term for the gauge field. That is exactly the important next point. So a gauge field with no kinetic term is a confining gauge field, right? That it's 1 over g squared times f squared, with g goes to Exactly. This is the microscopic description of the model, which is the right answer, right? Because microscopically, everything is made of electrons, right? And so the thing should be confining at short distances. So this is exactly the important point. There is no kinetic term for this variable a that we're integrating over. There's just nothing constraining it at all. It's just wildly fluctuating at short distances. But it's interacting with these parton variables. It spends half of its, or some fraction of its time as a pair of partons. And this vacuum polarization, or finite density polarization, generates dynamically a kinetic term for it. It generates a whole bunch of terms. And what terms it generates depends on the state of the partons. Right? This is the linear response of the parton state to this gauge field. It produces a kinetic term. This is at short distances. Okay, and so this means it's confined at short distances. And this story I'm telling you is interesting only if by this mechanism we produce some dynamics for that gauge field, which is deconfined or somehow otherwise interesting at long distances. So that these degrees of freedom are, which we're guessing, like in any duality, we're guessing some good set of degrees of freedom to use at low energies. All right, and then we check the guess by computing whatever we can compute. Okay, so now why did I choose nu equals a third? It's because of the following thing. So let me retreat for a moment from this lattice model to the continuum. So here's a picture that I want you to have in mind of. So here's the Planck scale of condensed matter physics. And okay, this is 1 over the lattice spacing, let's say. And then let's coarse grain a little bit, but still describe things in terms of the electrons. So this is electrons in the continuum. So I'm going to think about this electrons with the same kind of interaction in a big magnetic field, but in the continuum, where you all know this from basic quantum mechanics, right? Electrons in a big magnetic field, they form Landau levels. There's a big degeneracy of the Landau level, right? Okay, and nu equals a third is easy to explain. In that case, it means you filled a third of the Landau level. Okay, and then the question mark is down here. And well, I guess we know the answer, right? The answer is that we're going to get this topological field theory, this S of A at the end. And the question now is, how do we get there? And okay, so if we fill a third of the Landau level with free fermions, what is the spectrum of excitations? What degrees of freedom do we need to include at the lowest energies? Well, which third of the Landau level do we fill? Right? There's a huge degeneracy of which states we fill. And this degeneracy, this degeneracy is not protected by anything. And adding a generic perturbation, like this interaction term, is going to split that degeneracy. And the big question is how it splits the degeneracy. And here we've made a guess for what should happen. And here's the beauty of this guess. All right, this is important. I need to get some factors of 3 right. Here is the beauty of this guess. So 1/3, no, not in the black hole. 1/3 is the filling fraction of the electrons. Okay, and what I mean by that is that's the number of electrons divided by the number of orbitals in the Landau level, which is the number of flux quanta, which is NE over, okay, so some basic physics is EB area over HC. Okay, this B is the magnetic field, A is the area of the quantum Hall droplet. Okay, and so if we partially fill this thing, it's gapless. But now here comes the magic. The Fs have charge 1/3, right? Because 3 of them make a single electron, right? Electric charge 1/3, which means that if you put them in a magnetic field, their filling fraction is NF over the number of flux quanta for the number of orbitals in the Landau level for a field of charge 1/3, which is NF is the same as NE because each electron is 3 partons. And N5 over 3 depends on E linearly, and so this is 1/3 EBA over HC, which is 3 times nu E, which is 1. Okay, so that's the whole point of the 3. The whole point of the 3 is that at this filling, with this ansatz for the partons completely fill their Landau levels, which is a gapped state. It's an integer quantum Hall state with an energy gap. And the beauty of this is that I've already convinced you that this diagram, if these things are in an integer quantum Hall state, produces a Chern-Simons term for the gauge field, with a level which is related to the quantum Hall response as well, you guys worked that out, right? This thing lifts smoothly and gently lifts the wildly fluctuating degree of freedom that we included here. So the dynamics of this wildly fluctuating gauge field are quenched by the partons. And so here we can think about it this way. Here's the delta E of the partons. There's some regime in here where the physics is described by S of the partons in A, and then below here we get this Chern-Simons theory that we talked about last time. Okay, so this is an example of,
So
yes.
last time when you were talking about
Yes.
the current of a quasi-particle.
Yeah,
I can
it's
think
the
of it as
partons.
Fs.
Exactly. It's exactly the density, the current for the Fs, precisely. Beautiful. Okay, so this is an example of this is maybe a very happy example of the application of the parton construction. But the general point that I want to convey is that interesting states of matter that you can make this way correspond to phases of gauge theory, interesting phases of gauge theory, which are sort of the opposite of QCD, where at short distances they're confined, so they match on to the theory of electrons that we described here. Confinement of this gauge theory means you go back to the description in terms of the electrons. And at long distances, they do something else. They do something interesting. Okay.
Guess the wave function for that you derive the Lagrangian for, is that right?
Well, I've showed you how to derive it, yeah. Yeah. Yes, yeah, and right. So one thing I advertised as a reason to do this is that it tells you what the wave function should be. The ground state wave function should be, well, you look at the ground state wave function of the partons, which is, right? So it's the parton ground state, and then you project onto the you do the gauge projection, right, onto the satisfying the constraints, in which so with the parton ground state, here, let's write it in the electron coordinates. So Ri is the positions of the electrons. And well, what is this parton ground state? Well, you just fill their Landau levels. It's a Slater determinant of these Zij, Z's are complex coordinates on the plane. Product I less than J. There's some 1/3 somewhere, sum of Zi squared over the correct length. And then there's 3 of them, right? Each of the partons is doing this, and the gauge projection puts them all in the same place. The number of partons at each point is equal, and is equal to the number of electrons. And so that's why there's a 3 there. And this is the Laughlin wave function.
But he didn't do this, right?
He just wrote that down.
Just wrote that down.
Yeah. So there, yeah, okay. So I guess maybe the more general point I should make is that this construction, useful applications of this construction, correspond to ways that the fluctuations of the partons can keep the gauge theory from confining. And there are a few other qualitatively different examples of this. So for example, this mechanism that I've described here only works in 2+1 dimensions. But there are other ways you can keep a gauge theory from confining. For example, if you're in 3 dimensions, the Maxwell term can keep it from confining. That's something that can happen if you're in 3+1 dimensions. Another thing that can happen is you could imagine that the partons themselves are gapless, but in a stable state. Right? So for example, the partons could have a Dirac point in their dispersion with several species, and then the fluctuations of those partons can keep the gauge theory from confining. I guess it's worth mentioning in this context that perhaps something that's not obvious is that the reason that a further pressure in the direction of the gauge theory of confining is this argument due to Polyakov that even abelian gauge theory in 2+1 dimensions confines if the gauge group is compact. And that's because of the proliferation of monopoles. And the way to think about how the gapless partons can prevent that is that they attach 0 modes to the monopoles. And so the monopoles only contribute to higher dimension operators. And then such a state that I just described would be called something like an algebraic something liquid, where here the degrees of freedom are charge, it would be called an algebraic charged liquid. If they were spin, it would be an algebraic spin liquid. Now there's a more dramatic thing that partons can do, a way that the partons can be gapless in a stable way, which is they could form a Fermi surface. And then that's lots of gapless degrees of freedom, which are charged into this gauge field. And that really, really keeps the gauge field from confining. So Sung-Suk Lee gave a very convincing argument for this. And so such a thing is called a parton Fermi surface or a spin-on Fermi surface or something like that. And actually, maybe it's worth right now mentioning an example where that happens, which can happen with the same ansatz for the relationship between the electron and the partons, but where we imagine that the partons carry different charges. And so therefore, we can reach a different filling fraction. So let me just very briefly mention this. So actually, I already mentioned this state of matter in response to a question from Tom, which is suppose that we're at half filling. Suppose nu is a half. Then here is a way to, using that same relation, but actually without quite the SU3 symmetry. Suppose C is F1, F2, F3, but now I suppose that suppose that the electric charge of F1 is a half, and the electric charge of F2 is a half, and the electric charge of F3 is 0. So then, if this is and suppose that this is a new electron is a half, then that same kind of accounting, you can convince yourself, says that these two guys are filling their Landau levels. So nu1 is 1, and nu2 is 1. And so we can put these guys in integer quantum Hall states, and it's as if these two are combining to make a boson, integer quantum, sorry, not integer. It's a boson quantum Hall state with nu equals a half. So actually, that's just this wave function with a 2 here. If you put a 2 here, then it's symmetric under the interchange of the indices. It's a state of bosons, which also has a quantum Hall response. And then the point is that this is a gap state. This guy doesn't see the magnetic field. There's some finite density of these guys, which is equal to the number of electrons, and they're not in a magnetic field. So if I imagine that they're free, what state will they make? They'll form a Fermi surface. And this Fermi surface is coupled to a Chern-Simons gauge field. The gauge field that glues these guys together gets a Chern-Simons term because of this Hall response. And so this is a Fermi surface coupled to a gauge field. And well, maybe next time we'll talk a little bit about the dynamics that this produces. For the gauge field is something like, it depends a little bit on a few things, but it's well, it's a little bit interesting. So, okay, maybe I won't say anything about that right now. But it has the effect of this thing is a non-Fermi liquid. I guess maybe let me just draw this diagram. So the fluctuations of the gauge field, the effects of the fluctuations of the gauge field on the fermion propagator, kill the quasi-particle. Okay, so this is the wave function that you write down using this idea, which is you replace the third factor of this by a Slater determinant, a Slater determinant of plane waves, not of Landau levels, is the Halpern and Lee-Reed state. Okay, and this makes experimental predictions which have been verified. It's which is pretty cool.
Question.
Yes, please.
Could you compare and contrast? I was reading something about the same half-filling system that talked about thinking of it in terms of composite fermions.
Yeah.
The electrons grab
Yes.
2 units of flux each, and then there's no flux left.
Voila, the 2 units of flux. The 2 units of flux are exactly from these two guys.
So
Yes.
Okay.
Yes. So these bosons are gapped, right? And the thing we're doing here is attaching. So okay, they generate a Chern-Simons term for this gauge field, the one we've been talking about, and that Chern-Simons gauge field attaches flux to charge, right? And so it exactly attaches the flux from this quantum Hall response to that electron, and so it's the same picture. This is a sort of more microscopic description of that picture. Yeah. Okay, so I guess I'm getting close to the end of my time for today. I think maybe that was what I wanted to say about emergence of gauge theory. Did I say everything I wanted to say? If you think of other ways to keep the gauge field from confining, besides the ones I've listed, you should tell me. And then we'll find a new state of matter that's described by it. Okay. So the next thing I want to do, yes, please. Yeah. Yes. Yes. Precisely. Yes. Yes. Which, Exactly. I'm being too concise. Yeah, that is exactly what I'm trying to say. Yeah. Okay. Yes. Exactly. Thank you for the good summary. Okay. So then.
These things are sort of known by people in the lattice gauging community, although you almost have to be my age to know about them.
Uh-huh.
Typically only known by there are stories. That's the end of the statement.
I guess I should say that so I mentioned that a number of species of direct fermions in 2 + 1 dimensions can keep a U1 gauge field from confining. And the question of how many fermions is enough is one that's been a long... Exactly. It's one that people have fought like hell. And actually, something that's worth mentioning in this context, it's a timely thing to mention, is Tarun Grover recently wrote a paper using strong subadditivity of the entanglement entropy to constrain this number. In particular, he placed a upper bound on the number, which is something like 3 or something like that. So it's not that many. This is, I think, a very beautiful application of these ideas. I guess time is up, so maybe I'll stop here, and then next time I'll talk about S-sorcery a little bit and how to kill a Fermi liquid a little more than I did here. Yeah, okay, thanks. Time goes so fast. Do we have more questions? We have a discussion section. Discussion. You're here. We're not going to work on your homework problem. I have an answer.
I missed that.
Where did it come from?
Yeah.
Yeah. So do you want, well, so that's an equal sign there, right? So the idea is you write down the wave function describing the parton state as you know it, and to make the state of the electrons, you just have to project that parton state into the electron Hilbert space, which is accomplished by the gauge projection. And in this case, that's just a matter of setting the coordinates equal. The coordinates of the parton. So that's a position space wave function. Yeah, position space.